Between Mars and Jupiter there is a wide, quiet gap where many early astronomers expected to find a full-sized planet. Instead, when they finally searched carefully, they saw only points of light, thousands of small worlds scattered along one enormous, invisible ring. Tonight, on Misty Pulse X, we drift through that ring. We will unroll the story of the asteroid belt and the dwarf planets, not as background trivia, but as a slow investigation into why these fragments exist at all, and what they can still tell us about planets like Earth. Imagine looking down from far above the solar system. The sun burns at the center, the inner planets circle close in, and then there is this wide band of debris. Quiet light from the sun spills across that ring, a broken outline of a world that never formed on the page of space. To understand that sketch, we need to step backward in time, long before Earth had oceans or air. Our solar system began as a cold cloud of gas and dust, drifting within our galaxy. Something disturbed it, perhaps a passing star or the shock wave from an ancient supernova. Under gravity, that cloud slowly collapsed, growing denser near its center. As it shrank, it began to spin faster, like a figure skater drawing in their arms, and it flattened into a disk. Astronomers call this a protoplanetary disk, a thin, rotating sheet where new worlds can grow. Inside this disk, tiny grains of dust moved through the gas. When they collided gently, electric forces helped them cling together. Grains became pebbles, pebbles became boulders, and over a long span of time those boulders grew into mountain-sized objects called planetesimals, the basic building blocks of planets and asteroids. Near the young sun, where temperatures were high, only metals and rocky minerals could remain solid. Ices would quickly vaporize there. Farther out, the disk was cooler, so ice made of water, ammonia, and other simple molecules could survive, mixing with rock to form more fragile, frozen building blocks. This created a quiet zoning. Close in, mainly rock. Farther out, large frozen cores that would become the giant planets. Between these zones lay the region that would one day host the asteroid belt, a place where both rocky and icy ingredients were present, but where something kept interrupting growth. As one of those outer cores became Jupiter, its gravity began to dominate its surroundings. Every time a small body in the neighboring zone passed near certain paths, Jupiter tugged on it. Those repeated tugs nudged orbits into new shapes, keeping many objects from calmly merging into a single large planet. Collisions in that region did not stop, but they often became rougher. Instead of soft mergers, there were many high-speed impacts that chipped, shattered, or scattered material. Over millions of years, what might have become a single planet remained a swarm of leftovers, each piece following its own elongated track. Later, when astronomers mapped the spacing of the known planets, they noticed the curious gap between Mars and Jupiter. Some suggested there must be a hidden world there. For a while they called it the missing planet, as if the solar system were an unfinished puzzle with one piece absent. When the first object in that gap was finally seen, early in the 19th century, it was far too faint and small to be a normal planet. It was named Ceres, and soon others were found nearby. The puzzle piece was not a single world at all, but a whole population. From a distance, we still call this region a belt, but that word can be a little misleading. The main belt contains hundreds of thousands of known objects, yet space between them is huge. On average, individual asteroids are separated by distances so great that a spacecraft can cruise through with ease. Think of them as lonely houses along a very long rural highway rather than cars in crowded traffic. Each asteroid keeps to its lane, orbiting the Sun in a slightly different path. The belt is a system, but a very sparse one, more emptiness than stone, more quiet than collision. In that sparse family, certain members stand out. Ceres is the largest, nearly 600 miles across, and another body named Vesta is only a little smaller. Each held enough mass for its gravity to pull it into a rounded shape, smoothing out sharp edges over a long, slow time. Roundness matters because it tells us how gravity is working inside an object. When a body grows large enough, its own pull can overcome the strength of its rocks and ice, flowing material into a rounded form. Smaller asteroids cannot do this. They remain lumpy, like frozen fragments of broken hills. In the early 2000s, astronomers agreed on a new category, the dwarf planet. A dwarf planet orbits the Sun and is nearly round, but it has not cleared its orbital neighborhood of other debris. It is planet-shaped, but still shares its path with many smaller companions. Ceres in the main belt and Pluto in the distant Kuiper belt were placed in this group. They are not failed planets, and they are not ordinary asteroids. They are better thought of as small, complete worlds, each with its own history, quietly orbiting at the edge of most people's awareness. These dwarf planets and larger asteroids are important because they preserve materials from the early solar system. Earth has oceans, weather, and moving plates that recycle its crust. Small bodies have little of that. Many keep their ancient minerals and ices close to their original state, like samples stored in a deep freeze. Scientists sometimes call them fossils of planet formation. In the same way that a fossil bone shows you how a long-vanished creature once moved, a primitive asteroid can show you what kinds of minerals and organic molecules drifted here before Earth had a surface cool enough to stand on. Some of those molecules may have mattered for life. Fragments from asteroids and comet-like bodies still fall to Earth as meteorites. When researchers slice those stones open in clean laboratories, they find carbon-rich compounds and even amino acids, the small, flexible molecules that living cells use to build proteins. That does not mean life began inside an asteroid, but it does suggest that the chemistry needed for life was present in space long before the first oceans filled on our planet. One gentle idea is that impacts over long ages help deliver extra water and complex chemistry to the young Earth. While your body rests and your breathing settles, your small blue world continues its path around the Sun, guided by the same gravity that shapes the asteroid belt. There is something soothing in that repetition as planets, asteroids, and dwarf planets all follow patterns that repeat over spans longer than a human life. Compared with that, the motion inside your room is small and safe. Your blanket rises and falls slightly. Air moves quietly through your lungs. Far beyond your ceiling, Ceres and its neighbors are tracing huge, silent loops through space, arcs so large they could hold every orbit you have ever flown. When you picture an asteroid, you might imagine a jagged boulder. Many are like that, irregular and scarred with craters. Some are loose rubble piles barely held together. A few, like Ceres, have smoother, rounded shapes with brighter and darker patches that hint at ice, rock, and perhaps ancient movement inside. If you could stand on a modest asteroid, your weight would be almost nothing. A small hop might carry you in a slow, graceful curve across the surface. The horizon would feel close, and the sun would shine like a brilliant white disk in a sky filled with steady, distant stars. From that quiet perch, Earth would be just one pale point among many. Yet the rocks under your boots and the minerals inside your bones would share a common origin. They were forged in earlier generations of stars, those cosmic elders whose lives seeded the cloud that became our system. In a little while, we will follow how humans first detected these tiny moving points of light and how modern spacecraft have flown among them. For now, you can simply hold the outline of the mystery, a missing planet that never formed, and in its place, a ring of small worlds keeping very old memories. Astronomers of the late 18th and early 19th centuries scanned the night sky with a quiet determination. They were searching for order in the spacing of the planets, a pattern that suggested something might be missing between Mars and Jupiter. It was not proof, just a hint that invited patient watching. On the first night of January in the year 1801, Giuseppe Piazzi observed a faint point of light moving slowly against the backdrop of stars. It did not behave like a star. It shifted gently from night to night. He had found Ceres, the first known body in the belt. Soon after, others were discovered: Pallas, Juno, Vesta. Each new object deepened the mystery. Instead of one hidden world filling the gap, astronomers saw a growing family of small worlds, each following its own quiet orbit around the Sun. The 19th century became a century of patient tracking. With each new telescope, the list grew longer. Observers charted the paths of thousands of faint bodies, mapping a structure no one had expected: a wide band of rocky leftovers from the solar system's earliest days. For a long time, everything we knew about these objects came from dots of light and the slender clues they carried. Reflected sunlight hinted at their sizes and compositions. Small shifts in orbit revealed gravitational influences. But their surfaces remained unseen. That began to change in the latter half of the 20th century. Spacecraft could now leave Earth and show us what these worlds truly looked like. Cameras, spectrometers, and radio instruments replaced guesswork with direct, quiet measurement. One of the earliest close encounters came in 1991, when the Galileo spacecraft passed by an asteroid named Gaspra. It revealed an irregular, battered rock only about 11 miles long, covered with craters and ridges shaped by billions of years in space. 3 years later, in 1994, Galileo flew past another asteroid, Ida. There it made a gentle surprise discovery: Ida had a moon, a tiny body named Dactyl. This was the first confirmed moon orbiting an asteroid, a reminder that even small worlds can have companions. Then, in the early 2000s, the near-Shoemaker mission approached Eros, a large asteroid roughly shaped like a stretched peanut. After studying it closely, the spacecraft softly touched down on the surface, becoming the first probe to land on an asteroid. High-resolution images showed ridges, grooves, and scattered boulders. Eros was not a uniform stone. It was a record of impacts and fractures, a body shaped by time rather than by neat geological processes like those on Earth. As you lie there, it may help to picture these missions moving at their own slow pace. Each spacecraft spends months or years drifting toward its target, guided by small thruster nudges and the gentle pull of gravity. Nothing happens quickly out here. The next major leap came with the Dawn mission, launched in 2007. Dawn was designed to orbit not just one but two of the largest objects in the belt, Vesta and Ceres. Its ion engines produced a soft, steady thrust, allowing a graceful spiral from world to world. Dawn reached Vesta in 2011. From orbit, Vesta appeared bright and scarred, with a huge impact basin near its south pole. That basin, named Rhea Silvia, revealed enormous fractures and cliffs, signs of a collision that nearly reshaped the entire body. Vesta's surface held both ancient basalt and lighter material. This suggested it once experienced enough internal heat to melt and separate into layers, much like a miniature, unfinished planet. Dawn's data supported the idea that Vesta is a surviving fragment of an early protoplanet. After leaving Vesta, Dawn traveled on to Ceres, arriving in 2015. Ceres looked more muted, darker in tone, with scattered bright spots. The brightest lay within a crater, a basin filled with reflective salt deposits likely formed by water-rich brines reaching the surface. Ceres showed hints of internal activity long after its formation. Gravity measurements suggested a layered interior. Some regions may even have once held pockets of liquid water, warmed by the slow decay of radioactive elements. These details made Ceres feel more like a small, evolving world. While Dawn studied the belt, other missions explored different families of small bodies. One was OSIRIS-RX, launched in 2016, destined for the near-Earth asteroid Bennu. Bennu is a carbon-rich rubble pile, a loose collection of fragments barely held together by gravity. When OSIRIS-RX arrived in 2018, Bennu surprised researchers. Instead of a smooth surface, it was covered in boulders. During the sample collection maneuver, the spacecraft touched Bennu lightly, and the surface behaved almost like a fluid, shifting beneath contact. The sample returned to Earth in 2023, carrying grains of material unchanged since the dawn of the solar system. Inside those grains, scientists found water-bearing minerals and complex organic molecules, quiet evidence of chemistry older than Earth itself. Another mission, named Lucy, launched in 2021 to visit the Trojan asteroids near Jupiter. These objects shared Jupiter's orbit, gathering around two stable points ahead of and behind the planet. They are thought to be relics from the outer regions of the early solar system. Lucy's targets include bodies made of mixtures of rock, metal, and possibly carbon-rich materials. Each one may preserve a slightly different story about how the solar system assembled itself. The mission will unfold over many years, with flybys stretching into the early 2030s. Even now, farther out in the solar system, the New Horizons spacecraft continues its journey. After flying past Pluto in 2015 and revealing its mountains of ice and frozen plains, it traveled onto Arrokoth, a small, contact binary object formed from two gently merged lobes. Arrokoth's shape and smooth surface suggested it formed in a quiet, cold environment, where slow, gentle collisions allowed small bodies to merge without shattering. It is likely one of the most pristine objects ever visited, a direct link to the solar system's earliest conditions. Each mission adds another thread to the tapestry. Vesta hints at early internal heating. Ceres suggests frozen brines and chemical layering. Bennu carries organic compounds and hydrated minerals. Arrokoth preserves the calm merging of primordial pieces. As these threads accumulate, a new mystery emerges. If small worlds hold so much information about the early solar system, what do they collectively reveal about the formation of planets, water delivery, and the origins of organic chemistry? We will explore those questions soon. For now, hold the image of these spacecraft drifting among scattered worlds. Their cameras capture surfaces shaped by time. Their spectrometers read the subtle signatures of minerals. Their journey stitched together a slow, steady story of how planets grow and how some almost did. Up to this point, you have followed small worlds as quiet characters in a wider play. To see how they helped shape your own oceans, we can zoom in on something less obvious than craters or mountains, the journey of water itself across the young solar system. In the region where Earth orbits today, early temperatures in the disk were likely too high for much water ice to survive. Grains there were mostly dry rock and metal. To become a blue planet, Earth needed additional supplies of water from cooler, more distant zones. The asteroid belt sat close to that boundary, where ice and rock could mix. Many bodies there formed with minerals that locked water into their crystal structures. These are called hydrated minerals, and they turn up today in certain meteorites that fall quietly onto Earth. When scientists dissolve fragments of those meteorites and examine them with sensitive instruments, they find traces of water and a host of organic molecules. Some pieces belong to a class called carbonaceous chondrites, among the most primitive, chemically rich rocks we know. One gentle mystery is to match the fingerprint of that water to the water in Earth's oceans. Researchers look at the ratio of heavy hydrogen, called deuterium, to ordinary hydrogen. Different reservoirs in the solar system carry slightly different ratios, like distinct accents. For a time, many people imagined comets as the main bringers of water, icy messengers from the outer system. Some comets do have ocean-like fingerprints, but many have too much heavy hydrogen. Asteroid-borne meteorites, especially carbonaceous types, often come much closer. This suggests a picture in which a significant share of Earth's surface water may have arrived from the region of the main belt and beyond, delivered over millions of years by countless small impacts. Not a single dramatic event, but a slow, steady sharing of resources. To picture those times, imagine the young Earth not yet wearing blue oceans, still cooling from earlier heat. The moon had only recently formed. The inner system was busy, with leftover planetesimals on crossing paths. Impacts were frequent, yet spread over vast stretches of time. Some lines of evidence point to a phase called the Late Heavy Bombardment, when impacts may have briefly increased about 4 billion years ago. Others argue the pattern was more gradual. Either way, by the time stable oceans appeared, the surface had been stirred many times. When a water-rich asteroid struck, most of its material would vaporize, but some fraction of water and minerals could be incorporated into Earth's crust and atmosphere. Over repeated events, these contributions could accumulate, helping to fill basins and feed a growing ocean cycle. The same deliveries brought more than just water. The organic molecules found in meteorites include simple acids, alcohols, and even amino acids. They are not alive, but they are ready ingredients for chemistry that, under the right conditions, can become more complex. In laboratories, scientists simulate early Earth environments, warming mixtures of water, minerals, and simple organics, or letting them cycle through wet and dry phases. Under gentle energy sources like ultraviolet light or geothermal heat, more complicated molecules can emerge. Your own body is evidence that such chemistry works. Chains of amino acids fold into proteins. Rings of carbon and nitrogen form the bases of DNA. Many of the atoms in these structures spent long ages locked in dust grains, small icy bodies, or fragments from the belt. As you lie there, you might feel the warmth in your hands or the slow rise and fall of your chest. Inside each cell, water creates a medium where molecules can move, meet, and react. That same water once traced quiet arcs through space, part of clouds and ancient minor worlds. Not all of Earth's water had to come from outside. Some likely emerged from within, released as the planet's interior melted and minerals gave up trapped volatiles. The story that fits current evidence best is a blend, internal sources, plus many gentle deliveries from afar. In this blended view, the asteroid belt acts like a reservoir sitting just beyond the inner solar system. Gravitational nudges from Jupiter and Saturn occasionally send small pieces inward. Over deep time, a fraction of those pieces encounter Earth and leave a lasting mark. Even today, this process continues in a very quiet way. Each year, tens of thousands of tons of micrometeorites and dust settle onto your planet's surface. Tiny grains land on ice sheets, deserts, and the deep ocean, hardly noticed, yet still carrying traces of their origins. When researchers collect this cosmic dust from places like Antarctic snow or the roofs of city buildings, they find miniature versions of the same hydrated minerals and carbon-rich compounds seen in larger meteorites. The connection between belt and ocean has not completely ended. In the depths of the sea, far from sunlight, hydrothermal vents pour out mineral-rich fluids from Earth's interior. Some theories of life's origin focus on these sites. The chemistry there depends in part on minerals and elements delivered during the planet's assembly, including from small bodies. In that sense, the asteroid belt's influence reaches all the way to ecosystems that flourish without light, where bacteria and more complex creatures draw energy from chemical gradients. It is a distant echo of collisions that happened long before any ocean animal swam or any tree grew. When you drink a glass of water or listen to waves on a shoreline, you are hearing the calm result of many restless steps: star formation, disk evolution, asteroid growth, migration, and impacts. Each step left subtle signatures that scientists are still carefully decoding. Space missions add new clues to this picture. Samples from Bennu and Ryugu, measurements from Ceres, and spectra from many smaller objects give direct access to the materials that once orbited quietly beyond Mars. They help test whether our water story fits the actual ingredients. If future analyses find that some asteroid types match Earth's oceans especially well, the case for the belt's contribution will grow stronger. If they reveal surprises, models will be adjusted. In science, even a mismatch is useful. It points toward a better question to ask. For you, lying on your small blue world, the exact percentages may matter less than the overall feeling of connection. Your heartbeat, your thoughts, and the oceans that regulate your climate all belong to a chain that includes silent rocks drifting in the cold between Mars and Jupiter. Those rocks do not know they played a part. They simply follow paths set by gravity and chance. Yet, through them, elements were mixed, water was moved, and chemistry was seeded. Given enough time and the right conditions, that quiet process led to a planet where stories can be told. As you let your eyes close, you might imagine one small meteoroid entering Earth's ancient sky, glowing briefly, then scattering its minerals into a shallow sea. Over ages, pieces like that helped turn a rocky world into a watery one and, eventually, into a home for life like yours. While you rest, your breathing marks the gentle rhythm of life on Earth. Out in space, another rhythm continues, asteroids circling, dwarf planets turning, and robotic explorers gliding in long, patient arcs. Nothing rushes here. Everything unfolds on the timescale of worlds. In the next part of our journey, we step back and look at the larger picture. We will compare these small worlds to Earth, explore their roles in shaping our planet, and follow the quiet connections that tie your small blue world to the cold belt beyond Mars. Stand for a moment at a higher vantage point in your mind, above the plane of the solar system. You see the sun at the center, bright and steady, the planets as looping lanes of motion, and the asteroid belt as a faint, speckled band between Mars and Jupiter. Many of those specks are tiny, no larger than city blocks. A few are hundreds of miles wide. Each one keeps its own slow appointment with the sun, completing an orbit in a few years, or in the case of the outer belt, in periods closer to half a human lifetime. From this view, the belt looks like a borderland. Inside it, worlds like Earth, dry and rocky. Outside it, the giant planets with their deep atmospheres and rings. The belt sits at the frontier, a zone where rock and ice share space and history. When scientists study the belt, they are not only asking what it is. They are asking what might have been. If Jupiter had been smaller, if collisions had been gentler, could a full-sized planet have grown there, perhaps even with its own oceans and weather? That question leads them back toward Earth. To know why our planet carries liquid water, continents, and living cells, it helps to know what happened to its neighbors. The belt shows a version of planetary history that paused early, freezing some stages in place. Samples from Bennu, dust from comets, spectra from Ceres and other bodies all point toward the same quiet fact. Water, carbon compounds, and simple organics are not rare in our system. They are woven into many small worlds like threads in a shared fabric. On your planet, those threads have been drawn together and rewoven many times. Rain falls, rivers move sediment, plates shift, volcanoes erupt, life itself cycles elements through air, ocean, and rock. Much of the original pattern has been overwritten. In contrast, many asteroids are like old storage boxes that were never unpacked. Their minerals still hold the water locked into crystal structures. Their dark carbon-rich grains still carry simple organics that formed in cold, early environments before Earth existed. When researchers study meteorites in clean laboratories, they sometimes find amino acids and other complex molecules inside. These are not proof of life elsewhere, but they show that the chemistry life uses can emerge in the quiet darkness of space. It is possible that during the heavy bombardment phases of early Earth, countless impacts from asteroids and comet-like bodies delivered additional water and organic materials. Over millions of years, this could have helped tip Earth toward becoming a blue, living world. Imagine Earth without those contributions. Perhaps it would still have oceans, supplied mostly from within. Perhaps it would be drier, a more marginal place for life. The belt does not answer that fully, but it provides the ingredients list for the possibilities. As you rest, your own body quietly illustrates the outcome. Water fills your cells, salts flow in your blood, carbon structures your tissues. Every atom of those elements was forged long before humans, and some may once have traveled inside small, cold worlds. The connections reach even deeper. When scientists compare the isotopes of elements in meteorites to those on Earth, they can often match specific families of rocks to specific origins in the belt. It is like matching handwriting styles across letters sent from different towns. Those matches tell a story of exchange. Material from the main belt has fallen inward over deep time, while fragments from farther out have also visited. Gravity and chance have mixed the solar system, sharing resources between inner and outer regions. Meanwhile, the dwarf planets hold their own versions of this story. Ceres with its salts and possible past brines. Pluto with its nitrogen ice plains and towering water ice mountains. Each small world shows how similar ingredients can be arranged in very different ways. On Pluto, the ice that covers much of the surface behaves more like rock does on Earth, flowing slowly over ages, piling into ridges and blocks. Nitrogen ice can convect, lifting and sinking as heat from below shapes patterns in what seems, at first glance, frozen and still. On Ceres, bright patches hint that salty water once rose from inside, perhaps freezing quickly, leaving reflective deposits. This suggests that even small bodies can have internal layers, where pockets of liquid or soft ice may persist long after the surface has gone cold. These worlds are not likely homes for life as we know it, at least near the surface. Their atmospheres are thin or nearly absent, their sunlight weak. Yet they show that complexity is not limited to big, warm planets. Even distant fragments can rearrange themselves in rich ways. When you look up at a night sky from a backyard in Arizona or a beach in Florida, the stars seem uniform, a simple scattering of lights. The belt and the dwarf planets remind us that behind that apparent simplicity lies an intricate structure of families and histories. The same gravity that keeps your feet on the ground also sculpts those families. It gathered the original cloud, spun the disk, nudged some regions into planets, and left others half-finished. The asteroid belt is one of the places where we can still see that half-finished work. This raises a gentle, larger question. In other planetary systems around distant stars, how common are belts like ours? Do many systems have borderlands of rock and ice where planets almost formed? Do they also host dwarf planets circling quietly at their edges? Observations with space telescopes suggest that debris disks are common. Around young stars, astronomers often see belts of dust that shine in infrared light. In older systems, gaps and rings hint at planets shaping the material, just as our giants shaped our belt. When we study the asteroid belt and dwarf planets here, we are learning a template. It is one example of how matter can arrange itself around a star. That template can then be applied outward, helping us interpret the faint, distant signals from systems we will never visit. In that sense, small worlds play an outsized role in our understanding. They help bridge scales, linking the experiences of meteorite grains in a microscope to the broad statistics of exoplanet systems observed across the galaxy. They connect the very small with the very large. In your own life, you may have noticed how small details sometimes reveal bigger truths. A single tree can hint at the climate of its region. One stone can show the history of a river. In the same way, a single asteroid's composition can hint at a whole region's past. Consider again Bennu. Its loose rubble structure tells us that it is not a solid block but a collection of fragments from earlier bodies. Its carbon-rich minerals and hydrated phases show that water once interacted with its material, even if Bennu itself never held oceans. That means somewhere in its history, perhaps on a parent body that later broke apart, chemical reactions between rock and water occurred. Those reactions can produce a range of organics and change the minerals, storing a frozen record of watery activity in otherwise dry space. Arakoth, by contrast, seems never to have been heated much at all. Its two lobes likely formed gently in a cold, outer region where collisions were slow. Its smooth surface shows little internal change. It is a snapshot of the earliest phases of accumulation. By comparing such objects, scientists can build a timeline. Cold, untouched bodies like Arakoth show the starting point. Altered bodies like Bennu show the next stages. Larger dwarf planets with layered interiors hint at more advanced steps along the path to full planets. Earth stands far along that path. It has melted, differentiated, and reshaped its surface many times. Life has altered its air and oceans. To understand how such a world can arise, it helps to have examples at each earlier rung of the ladder, preserved in smaller forms. As you listen, you might feel your thoughts drifting the way a spacecraft drifts between flybys, coasting most of the time, adjusting course only with small, gentle pushes. Learning about these worlds can feel similar, a sequence of small insights adding up over time. There is also a quieter emotional connection. Knowing that the water in your glass and the carbon in your muscles may once have been part of scattered pebbles in space can make the universe feel less distant. You are not apart from these stories. You are a continuation of them. Old stars forged the heavy elements. Clouds mixed those elements into new disks. Belts, dwarf planets, and comets stored and rearranged the material. Planets like Earth collected some of it, and life eventually emerged. Now, one branch of that life is looking back with curiosity. In this perspective, the asteroid belt is not only a ring of rocks. It is a chapter in a longer narrative about how complexity grows. It shows that even when a planet does not form, the leftovers can still shape the worlds that do and can still inform the minds that arise there. When future missions sample other asteroids or land on dwarf planets, they will add new pages to that chapter. Each core sample, each mass measurement, each high-resolution image will refine the story of how matter behaves when it is left to evolve under simple physical rules for long spans. On a more personal scale, there is comfort in those simple rules. Gravity, motion, and the interactions of atoms do not change from day to day. The same principles that describe a spacecraft's trajectory guide the arc of a tossed ball or the gentle fall of your chest as you exhale, knowing that stability can make the cosmos feel less overwhelming. Far from being a chaotic storm, it is a place where patterns emerge reliably, where belts remain in place, where dwarf planets return to the same part of their orbits over and over, like the ticking of a slow, cosmic clock. When you step outside at night, you do not see the clock's hands directly, but you sense the regularity in the paths of the planets and the cycles of the moon. Somewhere along those shared paths are the small worlds we have been tracing, keeping time in their own quiet way. In the next and final part of our journey, we will return to the present work of scientists and engineers. We will look at upcoming missions, new telescopes, and the ways in which the asteroid belt and dwarf planets may shape the future of exploration and, gently, your own world. Right now, you are living in a rare moment. For centuries, the asteroid belt and the dwarf planets were only faint points of light on star charts. In just a few decades, they have become detailed landscapes, with names, maps, and quiet stories written in ice and stone. Powerful observatories orbiting above the blur of Earth's air watch these worlds in infrared and visible light. Ground-based telescopes on high, dry mountains add their own long exposures. Together, they trace orbits, measure brightness, and notice subtle changes over time. At the same time, new spacecraft are on their way. One mission, named Lucy, is traveling toward swarms of asteroids that share Jupiter's orbit, the Trojan families. Each target is a fossil from the early outer solar system, waiting patiently for its brief, close visit. Another craft, Psyche, is headed for a metal-rich asteroid in the main belt. That target may be the exposed core of an early protoplanet, or a fragment of one. By circling and measuring it, scientists hope to see what the hidden hearts of rocky worlds might be like. In laboratories on Earth, grains from asteroids already rest in clean containers. Samples from missions like OSIRIS-REx and Hayabusa have been divided and catalogued. Some are studied now, others are stored carefully for future scientists with tools we have not invented yet. There is something soothing about that long view. A small grain of dark stone can sit quietly in a drawer for decades, waiting. When a new instrument is finally ready, that grain may reveal a detail about water, organics, or early heating that no one could see before. Small worlds also play a role in a different kind of experiment. One recent mission nudged a tiny moon of an asteroid, changing its orbit by a small amount. It was a test, a proof that gentle, controlled pushes can adjust an asteroid's path without drama or haste. The purpose of such work is not to stir fear, but to extend our choices. Knowing how to alter the course of a small body, even slightly, turns asteroids from distant curiosities into objects we understand and can, if needed, manage with care over long stretches of time. Looking farther ahead, some researchers imagine using asteroid resources in future centuries. Metal-rich bodies could one day supply materials for structures in space. Water-locked-in minerals could become fuel and life support. For now, these ideas remain quiet plans. Whether or not those plans are realized soon, studying these bodies changes how we see value. An object once thought of as a random rock becomes a detailed record of early history, a potential source of insight, and perhaps, far ahead, a resting place or way station. As you listen, teams on the night side of Earth are awake in control rooms and observatories. In California, in Texas, in Florida, and beyond, people watch streams of data about orbits, spectra, and images, tracing the motions of worlds you may never see directly. On their screens, numbers and plots appear as lines and curves. To them, a slight change in brightness or a shift in color is a sign of rotation, surface texture, or composition. They are reading the silent language of light that has bounced from distant rocks to their detectors. In the coming years, wide-field survey telescopes will scan the sky over and over, mapping millions of asteroids with patient repetition. They will notice newcomers, refine paths of known bodies, and reveal families and clusters we have not yet recognized in the belt. Other instruments will study distant debris disks around nearby stars, looking for gaps and rings that hint at unseen planets. Each pattern helps test whether systems like ours, with belts and dwarf planets and small icy worlds, are typical or rare in the galaxy. The more we learn, the more a quiet pattern emerges. Earth is not the center of the universe, yet it occupies a gentle niche. It orbits in a band where liquid water can persist on the surface, shielded enough by atmosphere and magnetic field to support complex life. So far, among all the worlds we have seen in detail, your small blue planet is the only one known to host forests, cities, oceans full of swimming creatures, and people lying awake, listening to stories about other worlds. That uniqueness can feel humbling and protective. Knowing that asteroids and dwarf planets helped shape this home does not diminish its specialness. Instead, it highlights how many steps were needed. From older stars to dust, from dust to fragments, from fragments to planets and oceans, and finally to living listeners like you. As you rest, you are part of that chain. Your heartbeat is one more rhythm in a universe full of cycles, from the spin of Ceres to the orbit of Pluto to the slow turning of the galaxy. None of these cycles rush. They repeat with a patience that far exceeds a single lifetime. You might notice the small details of your own environment now, the feel of fabric against your skin, the faint sounds in your room, the weight that gently anchors you to the mattress. The same gravity that shapes orbits holds you here, steady and safe, while you drift. When you think back over this journey, you may recall the first puzzle of the missing planet, the discovery of Ceres, the flybys and orbits of small worlds, the samples in laboratories, and the larger connections across space. Together they form one continuous, quiet arc. We began with a ring of fragments between Mars and Jupiter and followed it outward to dwarf planets on the edge of the Sun's domain. Along the way we saw how these modest bodies store memories of early times and how they may have contributed to the sea-covered world you inhabit. Now, as your thoughts slow, you can let the details soften. You do not need to remember every name or every process. It is enough to feel that you are resting inside a well-ordered system, one that has been unfolding since long before humans and will continue long after. If sleep comes, the story can continue in the background, like a distant spacecraft coasting along its trajectory after its engines are quiet. If you remain awake, you can revisit any part of this journey in your imagination, tracing orbits and surfaces in your own time. And if you ever wish to travel here again with MistyPulse, this path through the asteroid belt and the dwarf planets will be waiting. New missions may add details, but the core will remain: small worlds, quiet light crossing space, and your own life unfolding on a small blue world.